Very good job. So that's what we are going to see. And why it is important for you guys? You are going to make something, right? You are putting these bones together and going to make something. Why it is important for you guys? Come on, come on, come on. Is it important? You are aerospace engineering students. Why materials are so important for you?
It's important to understand what gives the properties of the material that we want.
Absolutely. You know, sometimes I get these comments at the end of the session. So we are aerospace engineering students. Why we learned all these things? That's the reason why, exactly why you are learning it. Basically because you are aerospace engineers and you are supposed to use aerospace materials. And if you don't know what are the properties of aerospace materials, how can you engineer a structure? Can you? Can you?
Not well.
Not well. Absolutely not well. So that's the reason why we are learning this one. And okay, we are going to mostly in this class we will talk about only the metals and alloys. Okay, and here we are going to learn only about the metal, the close packing in metals. Close packing in metals. And you know, in the last class we talked about different types of materials. One is the metallic solids, other one is the ionic solids, and the third one is covalent solids. And what is the difference between them? Metallic solids, you know, those are metallic solids, and you see a extended network of atoms held together by metallic bonds. By metallic bonds. And then ionic solids, ionic bonds. And what about covalent? Covalent bonds. And what about the directionality of these different types of bonds? Which is directional and which is not directional? Covalent is directional. Metallic and ionic bonds are non-directional. Very good. So now we talked about the close packing with respect to energy, and I said that it is important. Why? If you look at the energy of this one, that is the interatomic distance versus the energy, potential energy for the randomly packed one. Look at this one, this is where the energy is. Where it should be the ideal energy, it should be here, somewhere here, for the complete close packing of your material. Agree? It should be at the bottom. So that is the difference. And then here you have an ordered packing, where you have the bond energy at the bottom of that curve. That is the ideal bond energy for that human material. Now, today we are going to talk about more things, material packing. Now think about it. It's a Rubik's cube, as you know. And you know, we have a number of these square cubic structures. Imagine that you have a number of these cubes. And you know, if you put them together, if you have a box or something and if you put all of them together, how efficiently that packing will be. You are just putting it together, okay? All the, you have 100 Rubik's cubes or 50 Rubik's cubes or whatever number, you are putting them just like that one. And the second case, I have the same box here. I am putting it one by one in a very ordered structure. Okay, one by one, sidewise as well as on top. In which case will you get more of these Rubik's cubes?
When you put them in the box orderly.
Orderly, absolutely. Agree? You can just imagine that. When you put just all of them dump into that box and put them one by one, putting them one by one, will give you a very ordered arrangement, as well as your packing is much more efficient. And what about the density? Density will be higher. That's what we are going to talk about now. Okay, so silicon dioxide, silicon SiO2, silicon dioxide, silicon and silicon dioxide. What silicon, you know, silicon is the material of choice for all the transistors and all your devices. And what this SiO2 is that the oxide layer or oxide of that silicon. And these are very important components in electronics, silicon and silicon dioxide, in making transistors. But you know, when you talk about the crystalline silicon dioxide and crystalline silicon dioxide, what is the meaning? Crystalline silicon dioxide means that there is a complete ordering of the atoms in your crystal. Complete order of the atoms in the crystal, which means that you are packing it like this one by one in your material, very completely ordered. Okay, imagine it in your mind, complete ordering of the atoms in your material. That is a crystalline form. And when you put them together, an example is that crystalline is a quartz. You heard about quartz, right? Quartz is a completely crystalline silicon dioxide. And the amorphous silicon dioxide, that is the other one. So non-crystalline materials. If you look at this one, here you see, unlike the other one, this is the same material, silicon dioxide. This is non-crystalline silicon dioxide, which is silica. And you know how atoms are arranged in a non-crystalline silicon dioxide. They are randomly packed in this material. That is the difference between these two words, crystalline and amorphous. Crystalline, complete ordering, and amorphous, it is a random packing of the atoms within your material. Okay? So,
Professor, could you switch to the
I will. Okay, thank you.
Yes.
So we are talking about the metallic crystal structure. As I talked, we are not considering that oxide. We are just considering metals like iron, copper, silver, chromium, molybdenum, whatever the metal is. Okay? We are just considering these metals, and we are looking into how atoms are arranged in this metal. Okay, how atoms are arranged in this metal. So which means that in these metals you can see a close packing. Why atoms are close packed in these metals? Because to minimize that energy. Whenever there is order, the energy is minimum, right? When you think about it, when you are sitting in an ordered fashion, if somebody comes in, they can easily get into the space. But when all of you guys are crowded, okay, not in an orderly fashion, it is harder for people to come in and join us, right? Very similar. Very similar. So we have that close packing. Atoms in metals tend to close pack. And that is called the close packing of atoms in a metal. Close pack structure. You are going to see the close pack structure. Got it? That is the meaning of the close packing. So, the reason for only one element is only one element is present. So what is the effect of that one? Only one element is present. That means if it is iron, only iron atoms are present. What is the relevance of that one? Because when only one element is present, all the atoms are of same size. Agree? Atoms are of same size. And what about the directionality of metallic bonds? Non-directional. So the nearest neighbor distance should be minimum. Agreed? Minimum to decrease the energy, to attain the minimum energy. So, as I said before, this is the ionic core. Metallic bond is nothing but ionic core in a sea of electrons. You need to imagine you are putting it in this ionic core into a sea of electrons, and in that sea they are close packed. But you know that ionic core, what is the charge? Positive charge. So they repel each other, but that is shielded by repulsion between the ions. Ionic cores are shielded by what? Sea of electrons. Sea of electrons. So you need to imagine it like that one. There is sea of electrons in between, but they are all close packed. In the for the sake of convenience, we assume that these ionic cores are touching each other to study the structure. Okay, these ionic cores are touching each other. When you put them together, what happens? They close pack, and close packing the atomic structure, and there is always, remember, electrons are in between, and we assume, again this is assumption, we assume that these ionic cores are touching each other. Electron cloud shield the ionic core. Okay, so there are two types of close packing to minimize the empty space. One, this is one thing. You can see that each of these atoms are surrounded by 6 other atoms. Versus you see here in this case, each of these atoms, for example, it is surrounded by 1, 2, 3, 4. Okay, so here look at this one. It is surrounded by 1, 2, 3, 4, 5, 6. This is the, now you are going to stack other atoms on top of this one. And either on top of this one or on top of this one. Okay, you need to assume it like that one. So then you get something called a unit cell. Okay, the unit cell, again important. So what is a unit cell? What is a unit cell? Yes.
As far as I understand, a unit cell is a cell which you can repeat again without any displacement that could reproduce a pattern of exponential.
Whole crystal. Okay, very good. So what he said is that when you look at some of these methods, or these close packed structures, you can see a certain pattern. Okay, I will show you a video later on where you can clearly see how the patterns are designed. Okay, and these patterns repeat over and over again throughout the crystal. Got it? When you look at this one, when you look at the atoms inside the crystals, you can see a very good arrangement of these atoms, close packing. And if you look at this close packing, you can see a certain pattern that repeats over and over again throughout the crystal. And the single unit of that pattern is called a unit cell. Okay? Single unit of that pattern is called a unit cell. So unit cell is a repetitive pattern, you can see. Pattern you can see in the crystal. So, another term you need to be aware of is the parallel pipeline. What is the meaning? You learned it in your math. What is the parallel pipeline? Yes.
The extension of a side deformity
Parallel pipeline is any structure where you have three parallel planes. So this is the one parallel plane. You see, this is that cube, or it can be a rectangular type structure, or whatever the structure is. You see what happens? This is one parallel side structure. So this is another one, and this is the third one. If you are given a given structure, you can assign these planes like this one. This is a parallel pipeline. Okay, so unit cell is a parallel pipeline. Okay, like that way, it is made up of that parallel pipeline structure, and the unit cell, important point, it represents the symmetry of the structure. Symmetry of the structure. What is the meaning? The repetitive pattern. Symmetry, repetitive pattern of that structure. So unit cell is very important. Now we are going to talk about talk in terms of these unit cells. Okay? Remember, this is the repetitive pattern you can see in your material, in your method. That is a unit cell. So don't worry about it. You will see a video where it is clearly, you can see how this repetitive pattern can be assigned. And also remember, here, if you look at this one, you see here is a unit cell. You see this this is the unit cell. Okay, the whole thing is the unit cell. And you look at this one. This corner is at the center of an atom here, right? And this corner is again, it is a center of an atom, another atom. Here it is another atom, here another atom, here another atom, here, and also same at the behind, at this corner, okay, somewhere here. Got it? So corner atoms, the corners are at the center of atoms. Okay? So, now if you look at that crystal lattice, there is another term called a crystal lattice, and 2 or 3 dimensional array of points coinciding with the atomic positions, okay, where the atoms are present. Such a representation is similar to the other one. Such a representation is a crystal lattice. Here it is the representation. Okay, so lattice parameter, another term we typically use. Lattice parameter, for example, in this case, if this is one unit cell, if you consider one of this as the unit cell, so this is a side, one side. And we can consider this as a lattice parameter. in this case, if you consider the unit cell, a side, one of the sides, we consider it as a, it is a lattice parameter. Usually, that lattice parameter is lowercase a, letter A, lowercase. And you know that for a cube, all these sides are equal. So all the length of the sides are A. Agreed? For a cubic unit cell. So that is called the lattice parameter. And then if you look at the metallic structure, if you take a metal like chromium, iron, cobalt, or whatever your metal is, you can see a close packing. And if you look at that close packing, there can be three types of close packing, cubic close packing. Okay, three types. Are you with me? When you look at the crystal structure, you can see the repeat patterns, and there can be three types of repeat patterns, cubic repeat patterns. In some of the metals, I am not saying all the metals are the same. Okay, in some of the metals, you can see these types of close packing. And these are called cubic close packing, and one is called simple cube or cubic structure. And the second one is called body-centered cubic method, and the third one is called face-centered cubic structure. Okay, the simple cube, body-centered cubic method, and the face-centered cubic method. From the name itself, it's very clear. What is a simple cube? In a simple cube, you can see atoms only at the corners. Okay? You can see, think about it now. So assume that this is very small, okay? And there is an atom at the corner here. Okay? Imagine that the center of this atom coincides with this corner. So you can have one atom here, another atom here, another here, and so on. Such a unit cell is called a primitive cube or simple cubic structure. Simple cubic structure. So the second one is called the body-centered cubic structure. And what is body-centered cubic structure? Now you can imagine what is a body-centered cubic structure. From the name itself, you have a simple cube, and you know that for a simple cube there is an atom. This corner coincides with the center of this atom. In addition to all those atoms, there is another atom at the center of this cube. Okay, there is another atom. Imagine this atom is at the center of this cube, and that is called a DCC structure, body-centered cubic structure. DCC structure. Clear? Any question? So the third one is the face-centered cubic structure. So tell me, what should be the face-centered cubic structure?
There are also, in addition to the corner atoms and the center atom, there are also 6 other atoms along the edges of that unit cube at the center of each face.
At the center of each face.
There isn't a center.
Not the edges, but at the center of that face. Is there any question?
There's no center atom in the middle.
There is no center atom here. There is no center atom for the face-centered cubic structure.
Okay.
There is no the center atom for the face CC structure. Only at the face centers. Sorry, don't be confused. What I said is compared to the simple cube, not to the body-centered cube. Okay? When you construct the simple cube, you have atoms at all the corners. In addition to that, there are atoms at the face centers. And that's the reason why they are called the face-centered cubic structures. Okay? Face-centered cubic structures. So here, a simple cubic structure, there is something called the coordination number. This is the simple cubic structure. And there is something called coordination number, which is coordination number is nothing but the nearest neighbors. Number of nearest neighbors, that is called coordination number. So if you look at the simple cubic structure, you can see that each of this atom is surrounded by 6 other atoms. You see 4 atoms in the same plane and 1 atom at the top and another atom at the bottom. So the coordination number of simple cube is 6. Now let's see if we can watch that video so that whatever we learned so far we can get an idea about it. If you still have any questions.
If you could travel within a crystalline solid, you would see the particles, atoms, ions, or molecules arranged in a regular array. Here, the spaces are greatly exaggerated, but in reality, the particles are packed close together. The unit cell of a crystal structure is the smallest portion that defines the structure. Stacking unit cells next to each other in all 3 directions gives the structure. Many elements and simple compounds have unit cells from the cubic crystal system. Let's examine the 3 types of cubic unit cells. All cubic unit cells have particles at the corners of a cube. The simple or primitive cubic unit cell has particles at the corners only. In reality, the particles lie as close to each other as possible. Note that the particles touch along the cube edges, but not along a diagonal in the face or along a diagonal through the body. By slicing away parts that belong to neighboring unit cells, we see that the actual unit cell consists of portions of the particles. When the cells pack next to each other in all 3 dimensions, we obtain the crystal. If we fade the others out, you can see the original group of 8 particles within the array and the unit cell within that group. We find the number of particles in one unit cell by combining all the particles portions. In the simple cubic unit cell, 8 corners, each of which is 1/8 of a particle, combine to give 1 particle. A key feature of a crystal structure is its coordination number, the number of the nearest neighbors surrounding each particle. In a simple cubic array, any given particle has a neighboring particle above, below, to the right, to the left, in front, and in back of it for a total of 6 nearest neighbors. The body-centered cubic unit cell has a particle at each corner and 1 in the center, which is colored pink to make it easier to see. With full-size spheres, you can see that the particles don't touch along the edges of the cube, but each corner particle does touch the one in the center. The actual unit cell consists of portions of the corner particles and the whole one in the center. 8/8 give 1 particle, and the one in the center gives another for a total of 2 particles. In this tiny portion of a body-centered cubic array, you can see that any given particle has 4 nearest neighbors above and 4 below for a total of 8 nearest neighbors. The face-centered cubic unit cell has a particle at each corner and in each face, which are colored yellow here, but none in the center. The corner particles don't touch each other, but each corner does touch a particle in the face, and those in the faces touch each other as well. The actual unit cell consists of portions of particles at the corners and in the faces. 8/8 at the corners gives 1 particle. particle in each of 6 spaces gives 3 more, for a total of 4 particles. In this tiny portion of a face-centered cubic array, notice that a given particle has 4 nearest neighbors around it, 4 more above and 4 more below, for a total of 12 nearest neighbors. Stacking spheres shows how the 3 cubic unit cells arise. Arrange a layer of spheres in horizontal and vertical rows. Note the large diamond-shaped space among the particles. Placing the next layer directly over the first gives a structure based on the simple cubic unit cell. Those larger spaces mean an inefficient use of space. In fact, only 52% of the available volume is actually occupied by spheres. Because of this inefficiency, the simple cubic unit cell is seen rarely in nature. A more efficient stacking occurs if we place the second layer over the spaces formed by the first layer, and the third layer over the spaces formed by the second. That simple change leads to 68% of the available volume occupied by the spheres and a structure based on the body-centered cubic unit cell. Many metals, including all the alkali metals, adopt this arrangement. For the most efficient stacking, shift every other row in the first layer so the large diamond-shaped spaces become smaller triangular spaces, and place the second layer over them. Then the third layer goes over the holes visible through the first and second layers. In this arrangement, called cubic closest packing, spheres occupy 74% of the volume. Note that it is based on the face-centered cubic unit cell. Many elements, covalent compounds, and, as you'll see in the next 2 examples, ionic compounds adopt cubic closest packing. Sodium chloride adopts the sodium chloride or rock salt structure. In this arrangement,
so, what is the coordination number? Nearest neighbors. Quiz question. What is the coordination number for BCC structure?
6. No. 8.
You just watched the video, right? It is H. Remember this. These are the questions that can be asked in the quiz. So what about the FCC, face-centered cubic structure? 12. And what about the simple cube? 6. So, you know, you have seen that the close packing of that was really nice, right? The cutting of free. That's the reason why I selected this video so that you can get a very good idea about how simple cubes are formed. So I hope you got it. You know, when you slice it, how you can get that simple cube. It's a beautiful video showing that that unit cell. So now you can see again the coordination number is 12. Now coming to this one, the cubic structure. Think about one cube. The simple cube is not efficient. Only polonium is polonium method. Polonium shows that close packing. Okay, only polonium. You can see that it is not efficient. That's the reason, right? and only 52%, 0.52. That is the packing factor. We are coming to that one of that simple Q. Okay, and then if you look at this one, the number of atoms per unit cell for cubic close packing. Why we are talking about this number of cells, number of atoms in a unit cell? Think about it. Here, this unit cell, there are atoms at corners. You need to imagine there are unit cells on top of it, at the bottom, on the sides, and on the sides, here, on top, and bottom. Now imagine that there is an atom here. This atom is shared between how many unit cells?
4 in total. No, 8 in total.
Any other answer? Think about it. Thinking machine. Use your thinking machine. You need to have imagination for this one, for this crystallography. So there is we are considering this atom, okay? This corner. 4 unit cells here. Agree? In the same plane, and 4 unit cells on top. So it's going to be shared between how many unit cells?
8.
8. And what about an atom at the face center?
It will be shared by 2 units.
2 unit cells. One, this one, and another one here. Agree? So face-centered atoms are shared between 2 unit cells. And what about if there is an atom at the center of this unit cell?
Only 1.
Only one. Very good. That's exactly what is given here. So you can determine the number of unit cells from this equation. N is equal to Ni, which is the interior atom, Nf, which is the face-centered atoms, number of face-centered atoms, and Nc is the number of corner atoms. So that is the equation, and it is required basically because when you consider the first, let's consider the face-centered cubic structure. So total, let me tell me the total N for the simple cube. What is N? Simple cube?
1.
Simple cube 1. And what about BCC?
2.
2. What about FCC?
4.
4. So that is FCC, interior atom, 0. What is, how many face-centered atoms? 6. 6 over 2 is equal to 3. And how many corner atoms? 8. 8 over 8, 1. So total is 4. So BCC, you know that all the corner atoms constitute 1. That is NC over 8 is 1. And Ni is equal to 1. And for the simple cube, there are only NC by 8, 8 over 8. That is 1. So we have already seen this structure, face-centered sequence. There is a first layer and followed by another layer. This is an ABC stacking. So you can see that this is the first layer. You can have this B-type voids here, okay? B-type voids, that is vertex pointing up, B, and the other one pointing down is C. If you consider this as B and this is C. And the nest layer, the first atom of the nest layer, either it can be on B, the crevices formed between these three atoms, that is the B, or it can be on C. Okay, now look at how the next layer is arranged or added. It is put on top of B crevices. See, on top of the B, it's going to lead to this such a layer. So look at this one. This layer is different from the first layer, right? Second blue layer is different from the green layer. Basically, there are no atoms exactly below this blue atom. Got it? Are you with me?
Yeah.
Okay, then what about the next layer? If I put the put on top of that C crevices, you can get that C layer. Now look at this C layer. Is there any atom at the bottom of this C, either a B layer or A layer?
No.
No. So we can call it as ABC, ABC. Then the next layer is going to be similar to the first layer. So such an arrangement, this is called ABC, ABC, ABC type closed pattern, which can lead to face-centered cubic structure. That's what we have seen in the video. Okay, this can lead to face-centered cubic structure. So, any question? So that is the face-centered cubic structure. Now we are looking at the atomic packing factor. So what is atomic packing factor? APF.
It is the volume of atoms in a unit cell over the total unit cell volume.
Okay, very good. So again, unit cell. Atomic packing factor, we determine the atomic packing factor as you have the volume of this unit cell. What we are trying to, from the name itself, atomic packing factor. How efficiently atoms are packed with respect to volume. Right? We are talking in terms of volume. So then it should be volume of the atoms present in this unit cell over the total volume of the unit cell. Isn't it? Agreed? The volume of the atoms present in this unit cell over the total volume of the unit cell. That gives you the atomic packing factor, which we can translate to how efficiently atoms are packed in your unit cell. We have seen in the previous one, simple cube, it is inefficient because atomic packing factor in that case is only 0.52, which means that only half of the volume of this unit cell is occupied by the atoms. Okay, that is the meaning. Now we are looking at the atomic packing factor of so this is the volume of atoms in the unit cell over total volume of the unit cell. So if you consider simple cube, so what should be the atomic packing factor? The number of atoms, we have already seen it is 1. And what is the volume of an atom? If R is the radius, right? 4/3 pi r cube. So, but if you look at this unit cell, you can see that this is a unit cell and these two corner atoms touch each other along that edge. So this is A. I I said previously A is called the unit cell parameter, that's the side length. This is A, and therefore we can write that A is equal to 2R, because this is radius of one atom, this is the radius of two atoms. Or we can say that R is equal to 0.5A. Okay? Because this is 2R is equal to A, R is equal to 0.5. That's the reason why we can get this is 0.5A. R, we can substitute it as 0.5A. So we can see what is the volume of the unit cell? A cube. So this is A cube, volume of the unit cell. Therefore, we can get the value, atomic packing factor for a single cube is 0.52. Okay, this is the 0.52. That is the atomic packing factor of a single cube. Now, the atomic packing factor of a face-centered cubic structure. And we have already seen a face-centered unit cell, you know, how many atoms are there? 4 atoms per unit cell. For a face-centered cubic, for a unit cell, 4 atoms are there. And if you look at here, you know, this is A, and this is also A. This is the unit cell parameter, this unit cell side. And if this is the triangle root 2, this hypotenuse is the square root of 2A. We can get this as 4 into 4 over pi r cube over a cube. That is the equation. 4 into 4 by 3 pi r cube over a cube. That is the volume of atoms in the unit cell over the total volume. So how we are going to do it? What is the volume of atoms? over 3, 4 into 4 is the number of atoms into 4 over 3 pi r cube. So volume of now the close packed directions. Okay, if you look at this one, we can write it as along the hypotenuse there are how many? What is this one? This is 1r. This is total is 2r within this atom, and this is 1r. So we can write it as 4r is equal to square root of 2a. Okay, 4r is equal to square root of 2a. So therefore a is equal to 2 root 2r. Agreed? Agreed? 2 square root of 2r. Now, volume of the unit cell. What is the volume of the unit cell? Volume of the unit cell is a cube, which is equal to 2r square root of 2 the whole cube. So which is equal to 16 r cube into square root of 2. So 8 into 2 into square root of 2, that is the 16 r cube into square root of 2. So now we can put the atomic packing factor. So atomic packing factor is equal to volume of atoms in the unit cell, which is 16 over 3 pi r cube over 16 r cube into square root of 2, which is 0.74. see that this is an efficient packing, right? Because almost 75% or 74% of your unit cell is occupied by the atoms. So this is an efficient close packing. So now BCC structure. So what about the BCC structure? Here you may need to find the touching atoms. That's the reason why you need to find the here a triangle with which are all the axes which are touching each other. So this is the touching atoms. So we can say this is root 3a along this axis, and and this is you need to imagine it is going through that unit cell. Okay, it is going through the central atom to this side. That is the unit cell. So from the 3D Pythagorean theorem, we can say that b squared, this b squared is equal to, what is the theorem? A squared, if this is one side, plus b squared, if this is another side, plus c squared. But in this case, since it is a cube, we can write it as b squared is equal to 3a squared. Okay, so we can, so what is B? So this B is 4R. So 4R squared is equal to 3a squared, and we can write it as 4R is equal to square root of 3a. Now, what is the atomic packing factor? Is equal to how many atoms? 2 into 4 over 3 pi r cube over a cube. Okay, from here you can substitute, you can find either A or R and substitute it and solve it. The atomic packing factor you can get is 0.6H. Okay, from here you either convert it to A or to the R and substitute here. You can solve this one atomic packing factor and you can get 0.68. The value is going to be 0.68. So now compare the atomic packing factor of FCC and BCC, face-centered cubic structure and body-centered cubic structure, which is going to be more efficient. Face-centered cubic structure, because 0.74, that is 74% of your unit cell is occupied by atoms, whereas only 68% of the unit cell is occupied by atoms in a body-centered cubic structure. An example of some of the face-centered cubic structure, it is face-centered cubic structure, the gold, silver, chromium, those things are all bodies, face-centered cubic structure, whereas chromium, I think chromium and certain iron, BCC alpha iron, okay, alpha phase of the iron, that is a BCC structure, example for a BCC structure. But the most efficient cross packing is face-centered cubic structure. Now, there is beyond that single cube, body-centered cube, and face-centered cubic structure, there is another important structure you need to remember, that is HCP structure, hexagonal cross packing. Okay, HCP structure. So this is the HCP structure. Okay, and you remember that how face-centered cubic structure is arranged. Initially, that green layer. Okay, then on top of the that one there is a blue layer, and if the third layer comes on top of this first layer, for example, the crevices formed by these three blue atoms. You remember I told you either it can be here or it can be here, right? So if the third layer is on top of this first layer atom, then it is a hexagonal close packing, HCP structure. HCP structure. The structure is here, you can see this is the first layer, this is the second layer, and this is the third layer. And here again the coordination number is very similar to the face-centered cubic structure, FCC structure. Coordination number is 12, and the atomic packing factor is same as that of the face-centered cubic structure. Okay, that is 0.74. Because you see the arrangement is more or less similar, except that this is AB type arrangement, whereas face-centered cubic structure is ABC type structure. Got it? So the packing factor is the same and the coordination number is the same. Okay? So coordination number is 12 and the atomic packing factor is 0.74. Cadmium, magnesium, tin, zinc, etc. shows this one. Do you want to see a video of this one? How this is arranged?
Yes.
To explain the body and structure of materials, we assume that the atoms are spherical. The spherical atoms can be put together in different arrangements. Some arrangements are more efficient ways of packing spheres than others. Cubic close packing is 74% efficient. 74% of the space is occupied by atoms, while 26% is empty space. Cubic close packing makes the most efficient use of available space. This is the first layer of a crystal with its atoms arranged in cubic close packing. Click on the second layer button to see how the second layer stacks in cubic close packing. The second layer of atoms stacks in pattern with the depressions in the first layer. Click on the third layer button to see how the third layer stacks in cubic close packing. The third layer stacks in the depressions of the second layer, but the third layer is offset from both the first and second layer. The third layer is occupying sites above half the depression.
This is the ABC, okay? Not that the HCP arrangement, not the hexagonal cross packing. What they are showing right now is the ABC tag.
The fourth layer stacks in the depressions of the third layer. The fourth layer of atoms has the same arrangement as the first layer.
Yes,
Even cell that results from cubic close packing is called a face-centered cubic unit cell because 6 atoms are occupying positions in the 6 cube faces. Now let's see how many atoms are contained within one face-centered cubic unit cell. Find within a cubic unit cell. A unit cell is 6 times 1/2 of the face atoms plus 8 times 1/8 for the corner atoms.
If you
No, unfortunately it's not there. That HCP is not there. So anyway, I assume that you can imagine that structure. Can you visualize it?
Yes.
Okay, so you have that, look at this one, this structure. You see the first layer, and these three atoms are completely inside that unit cell. And on top of which, you see, there are how many corner atoms? 1, 2, 3, 4, 5, 6. There are 6 corner atoms. And how many 6 corner atoms on top and 6 corner atoms at the bottom? How many center atoms? One here and another one here. Okay, and now this is the equation you can use to determine the number of atoms in the unit cell for a HCP close packing. N is equal to Ni, the number of inside atoms, plus number of free-centered atoms over 2, plus number of corner atoms over 6. So we can write it as N is equal to number of interior atoms, 1, 2, 3, therefore 3. Number of free-centered atoms, 1 on top and another at the bottom. So you 2 over 2 plus how many corner atoms? 6 plus 6, 12. 12 over 6 is equal to 12 over 6 is 2. So 3 plus 1, 4 plus 2, 6 atoms per unit cell. Okay? 6 atoms per unit cell. So we are going to see the reactions and plates and all those things. One thing you need to remember, again, you need to remember that, look at this one, HCP arrangement. Please listen here, it's important. You can see that it is made up of 3 parallel paper. Are you getting it? One here, this is the whole parallel paper, this whole structure. Then if you draw another line along here, between these 2 atoms, this is another parallel paper on this side, another on this side. Got it? Are you with me?
Yes.
Can you imagine? One here, already here, and just draw a line between these 2. You can see the second one on this side and the third one on this side. So that's the reason why it is made up of 3 parallel papers. And the side, okay, directions and all, I am coming to that one, so I will explain it. So unit cell, there are 7 crystal systems. We talk only about that cubic unit cells, cubic structure. But there can be other structures like this one, depending on the sides A, B, and C. Okay, now on you need to listen here very carefully. I told you, since our class is not that a cube or a canvas structure, it's otherwise it would have been very easy. Previously I used to say it like that one. But imagine our class is like a cube or a rectangle or whatever structure we have. Okay, just like 4 walls like this one. So our concept is, from now on, this corner, that corner on that side, that means this side of this room, that side, that is the origin. We consider it as the origin. Okay? Please remember it, that is the origin. And one which is pointing towards you, that is the x-axis. And one pointing in this direction, that is the y-axis. And one pointing up, that is the z-axis. One more thing, okay, I'll repeat it again. One towards you, x-axis. One in this direction is y-axis. One going up is the z-axis. So for this one, imagine you have another classroom exactly like this at the back. So if this is the x direction, positive x direction, one which is coming towards you is positive x direction, one which is going in that direction, away from you, that is the negative x direction. And if one in this direction is the positive y direction, one which is going in that direction is the negative y direction. So one which is going up is the c direction, plus c direction, or positive c direction. One which is going down is the negative c direction. Clear?
Yes.
Okay. So here in say, this is just you need to understand, but we are going to look at only the cubic system and external XCP structure. But you need to be aware that there can be 7 crystal systems. Okay, you need to know this one. There are a total of 7 crystal systems depending on the A. What is A? A is the dimension of this unit cell going in the x-axis, and B is the length of the side of this unit cell going in the y direction, and the C is the letter C for cat. That C is the length of the side of this unit cell going in plus n direction. Clear? But we know that for a cubic unit cell, this A is A itself, B is also for cubic is A, B is equal to A, for C is equal to A also. But we consider, from now on, we consider it as A, B, and C. Okay? So now this is 7 crystal systems are there. One is cubic, where A is equal to B is equal to C, alpha, beta, gamma is equal to 90 degree. The other one is tetragonal. A is equal to B, not equal to C, and alpha, beta is gamma is equal to 90, and so on. Just you need to go through it. What is the difference between cubic, trigonal, ortho, rhombic, rhombohedral, hexagonal, monoclinic, and triclinic? So, since the BCC and FCC belongs to the cubic crystal system, that's what I said. Here is the cubic unit cell, and HCP. Okay, HCP belongs to hexagonal system. These are the only 2 systems we are going to look at. Okay, this system, cubic system, and hexagonal cubic system. But you need to be aware of there are a total of 7 crystal systems. Okay, depending on A, B, and C, and the angles alpha, beta, and gamma. So, density. So, what is density of any material?
Density is mass per volume.
Mass per volume. Thank you. Mass per volume. So, what is the density of a unit cell? If you know the density of a unit cell, you can easily say what is the density of that material, right? Because metal is a repeat unit of that unit cell. So, how can you determine the density of the unit cell? You know that it is the mass of the atoms over the total volume of the unit cell, right? Total volume of the unit cell. And now we have learned how many atoms are there in simple cube, face-centered, body-centered, and so on. Now, what is going to be the density? You can easily tell me what is going to be the density of a body-centered BCC unit cell.
4 times the mass of
BCC.
2 times the
2 times
mass
mass of the atoms in the unit cell over total volume. So how can you determine the mass of an atom? What is the mass of an atom? You can easily remember, you don't need to remember that equation, that's the reason I'm telling you. What is the mass of an atom?
The number of protons and neutrons.
Okay, that's that's correct, but what I am talking about, what we know is only the, if you look at the table or books, we know the atomic weight. So how can you get the mass of an atom? Because what is the atomic weight? Atomic weight is the mass of how many atoms?
6.02 times
Avogadro number.
Avogadro's number.
So Avogadro, the mass of Avogadro number of atoms is the atomic weight. Therefore, you can easily determine the mass of one atom, which is the atomic weight over Avogadro number. So then, what should be the density? Density is equal to, theoretical density is equal to so density is typically represented by rho, mass of atoms in the unit cell over volume of the unit cell. So mass of the atom, we can, for a BCC structure, for example, BCC or FCC or a simple cube, it depends only, it differs with respect to the number of atoms. So 2 into mass of the atoms in the unit cell is equal to the atomic the atomic weight, which is represented by A, N, this is N, okay? For BCC it is 2, but we can write it in general, N into A over volume of the unit cell is A cube into Avogadro number, Na. Okay? Or in general, we can write it as the density rho is equal to Na over volume of the unit cell into Avogadro number, where N is the number of atoms in the unit cell. A is the atomic weight. And V is the volume, Vc, or V is the volume of the unit cell. Now, Na is the Avogadro number. That is, Avogadro number is 6.022 into 10 to the power 23 atoms per mole. So now, look at this one. We can say that this is a plot showing all the densities. Metals, the density of metals is the highest, followed by ceramics, followed by the polymers. And here you can see the graph. This is the density with respect to different materials. Metals, they have high density, followed by graphite, ceramics, semiconductors, and such things, followed by polymers. This is that ceramics, then followed by polymers and composites. The density is in between the metals and polymers. Why the density is highest for metals?
Because of the metallic bonding, because of the atoms.
Close packing.
Exactly.
Because of the close packing. Okay, the density is highest for the metals because of the close packing in the metals and large atomic masses, and the ceramics have less dense packing, often lighter than other elements, and polymers has the lowest densities. Okay, now these composites can be prepared by adding by mixing high density metals as well with the polymers, low density polymers. So you can get a density in between. Remember the composite I showed you in the first class or second class. You have a very light metal material which you can make it into a very tough material too by mixing these two things together, the metals and polymers. So there is another something else called a polymorphs and allotropes. Okay, what is the difference between what is polymorph? If a given material, an element or compound, okay, if a given material has a different arrangement, atomic arrangement, close packing, then they are called polymorphs. For example, I talked to you about silicon. Okay, silicon, and you can see different materials like quartz. Okay, silicon, the quartz and silica. And what is the difference in between these two materials? They differ in the arrangement of atoms in the material. That is called polymorphism. Two or more distinct crystal structures for the same material. It is called polymorphism. Quiz question. It's a good deal, right? I am telling you all the quiz questions in advance. Remember all these things, that's the reason. So that is the polymorph. So what is the allotrope? The same material itself, you know, the carbon, it has a graphitic structure and it has a diamond structure. Graphitic structure and diamond structure. So carbon shows different arrangement of atoms in the material. And that type of different arrangement for a given material, that is called the allotrope, and that is the element. That is the difference between allotrope and a polymorph. Polymorph is a material by itself, it's a compound like SiO2, silicon dioxide. It is a compound, right? Whereas allotrope, it is an element. If a given element shows different arrangements, crystal arrangements of atoms, that is called allotrope. Okay, so you can see that iron, allotropes can also be, you can say polymorph. They are also polymorphs. You can give the name polymorph for the allotropes too. It's the general name, but if it is just one element, a given element, like iron has alpha, beta, and gamma, you will see it later. And that property is called, for a given element, it is called allotropy. Okay, that property is called allotropy. Okay, let's stop here. Thank you.